Up, dudes? We're going to be starting up this lab trajectory one, and this is where we're going to be doing our labs. I know that you folks are all into this Nerf gun idea that I had to do a lab, and you know what? I'm totally into it too. But the problem is we don't have enough time or lab time to do it, because I want to do the bridge building exercise. I want to do all of these different kinds of competitions. We won't have enough time to do an awesome Nerf gun lab. So I wrote it up. No, don't, Jonathan, don't freak out, because what I did was I wrote it up so that way you can do it at home, and I'm going to show you how to do them all today. All right? Yep, what up, dudes, every time. That's just the way I start all my videos. What up, dudes? I don't know why I do it. All right, so for this one, you're going to need a Nerf dart or any other type of object. I think that for this time, for this demonstration, I'm going to use a, oh wait, no, let's do it like this, a steel ball bearing. Can you see the ball bearing? It's right here. It's a little piece of steel. That's a ball. Or a disc gun or whatever. This is due, I think this is due on Friday or something like that.
This isn't the Revolutionary War.
Yeah, no, Sierra, you don't need a Nerf gun for this lab. You don't need a Nerf gun for the next lab or something that shoots. But for now, you can use anything that you can drop, like a tennis ball or a golf ball or a basketball or whatever. Got it? All right. So let's go through this lab, and I'll show you folks how this thing works. Equations needed. This thing looks crazy. Oh my gosh, this looks like so much math that my brain is shutting down as we speak. It is turning into putty because I don't understand any of those equations. Actually, this is exactly the equation that I just showed you. All right, I'll tell you what. Looks like you guys are freaking out right now. I'll give you a second. You have 5 seconds. Scream, shout, yell at your computer, say, I'm freaking out. Go for it. Go for it.
You're testing right there. Should
Okay, you shouldn't scream, but they can scream. You got 5 seconds. Go. 5, 4, 3, 2, and 1. Okay, you've had your chance to freak out. Now let's get into it. All right. And apparently, freaking out just means you're like have a seizure on your keyboard and you're just like. Gah! Okay, you ready? Okay. So, are you freaking out with that equation right there? No. Look at the equation. Don't draw. Don't doodle. Look at the equation. Are you freaking out with that one, the one I have an arrow pointing to? No. Why not? Because that's the one we literally did. We literally just covered this. We spent 10 minutes talking about this one. And you told me that you weren't freaking out when you were looking at that. So, are you freaking out now when we're looking at that? Okay. Actually, Isabella, let me tell you this. There was this experiment done between Galileo and Aristotle that said the time at which an object hits the ground will be the same regardless of an object's mass. So Isabella is saying, wait a second, if I drop something heavy, it's going to hit the ground faster than if I drop something light. No. No. That's not true at all. That's hard to believe. I'll tell you what, there's a whole discussion on it, and you know what? That would be a really great video for you folks to watch. In fact, I'll look it up real quick. Hold on. Okay, YouTube.
Okay. Mrs. Lee.
All right, there's a, let's see, Falcon Feather Moon. There we go. All right.
Dude, what are you doing here?
I'm the new assistant tennis pro.
All right, there we go. All right, here we go. Okay. All right, so check us out. Falcon Feather Moon. Check that video out. That was the advertisement for the video, which I have no idea.
It.
Yeah, no, I'm spamming the video to you. Okay, it's like a minute long, but it's of an Apollo 15 mission. They have a dude who's dropping on the moon, and he's dropping a hammer and a feather, obviously different masses, at the same time, and they hit the ground at the exact same time. That's right, suckers. Hits the ground, same time. That's craziness. It's a feather and a hammer. And the reason why I love it is because when Galileo first proposes, he says, well, if you went to the moon and you dropped a hammer and a feather, it would hit the ground at the same time. Well, hundreds of years later, we actually went to the moon, dropped a hammer and a feather, and it was right. It was crazy. And it's funny, he goes, the astronaut says, well, it's appropriate because this is my falcon's feather. And I was like, wait, this dude has a falcon? That's pretty cool. And by the way, this dude was actually an astronaut, and I forgot what his name was. I don't think it was like Buzz Aldrin or something like that, but it was Apollo 15 mission. He was Captain something. Let's see. Here we go. It was Joe Allen. No, wait. Let's see. That was the dude's name. I forgot what the guy. Yeah, I think it was. No, I don't think it was Joe Allen, but it was. You can find that out. That's easy information to figure out. All right, cool. All right. Anyway, so back to the equation. We've been taking tangents. All right. We're talking about dropping an object to the ground. Got it? And of course, we're not talking about any air resistance whatsoever. So we're talking about dropping an object to the ground. What is my height final? How high is the ball going to be at the end of the experiment? It's going to be on the ground, which is also known as 0. Good. So I'm going to put a 0 in for h. Got it? Minus h naught equals, okay. If I simply take the ball, okay, and I drop it. Okay, watch, dropping it. Okay, wait, that was quick. Let me do it again. Dropping it. What is its velocity? What is its starting speed? Is it moving the instant I let it go? All right, is it moving right now? No, it's not moving. And then the instant I let it go, the instant my fingers leave, does it all of a sudden like speed up real quick? Does it have like this immediate velocity, boom, throw, you know what I mean? Going from the start? Or does it start to gain speed? Start to gain speed. So what is its initial velocity? That's my question. That's 0. Are we cool with that? Like, that's not freaky at all, right? Times t. Minus 1/2 g t squared. Got it? All I did was I kind of just put in 2 zeros. I put in the 0 for the height in the end, and I put in a 0 for the velocity in the beginning. Sound good? By the way, I'm just curious to know, what is 0 times t? Okay, fine. What is 0 times 5? 0. What is 0 times 40?
0.
What is 0 times z? 0. What is 0 times t? 0. So this is, actually, this whole thing is 0. Do you guys agree? And what is 0 minus h? Well, it's just negative h. I don't even need to write down the 0 anymore because it's just, you just have a 0 there. Whoop-de-doo. Does that make sense? So I have negative h naught equals negative 1/2 times g times t squared. Got it? Not everything is 0. I just got rid of the stuff that was 0. But the h naught, that wasn't 0. That means I start dropping this at a certain height, and that height is called h naught. It is under an influence of an acceleration, also known as gravity, and it falls for a certain amount of time. So that piece of information is not 0. I don't get rid of that. But I got rid of the other stuff that was 0. And that's not freaky to you, is it? Is it? Are you sure? It's not crazy? Okay, so check this out. By the way, there's one last thing I'm going to do. I'm going to multiply both sides by negative 1. So negative h times negative 1 is actually positive h. Does that make sense? A negative times a negative is a positive. Did you guys learn that in 7th grade? Okay, did you learn that in 6th grade? Okay, well now you know, Miss 6th grade. A negative times a negative is a positive number. Good?
Yeah.
Okay. But if I do something to one side, I have to do it to the other side, or else it wouldn't be fair. So I'm going to multiply the right-hand side of the entire equation by -1, making it positive 1/2 times g times t squared. Are we cool with this? Okay, so check this out. See this equation right here? It's not magic. It simply comes from our original equation. All right? So it's not something you're freaking out about. Are you sure? It's not that bad. This equation will tell you the height that something is if you know the gravity that something is at, time, and the time that it takes to fall. This is actually a super useful equation. I used to when I was younger in college and I was super buff, I actually used to rock climb every other day. I used to rock climb for 5 hours a day, all kinds of cliffs. Yeah. And what I would do is after I would rock climb, I would go and do this thing called cliff jumping. It was a lot of fun. This was up in the mainland, and you basically go and find a big cliff and you jump off it and land inside the water. And it was awesome. Okay. No, it wasn't base jumping. It was cliff jumping. And you had to be very careful with what you did. I always swam in the water before I just jumped. I didn't just jump into jump off a waterfall or anything. Could be rocks right underneath there, and So I would check the area out first, and then I would climb up the cliff, and then I would jump in. It was a lot of fun. Yeah. Not only would I die, I would probably DYE as in dye the ocean blue or red or something. I don't know.
Spelling.
Yeah, Isaiah, that's not how you spell die. Anyway, yeah. Faustine, I'm sorry, I got to finish at 12:15. I just feel like there's a lot I want to cover, and technically I'm allowed to go to 12:15 because that's when our class all usually finishes. So, sorry. All right. Okay, so check this out.
We just went over how to be scared.
Wait. All right, hold on. Let me finish what I was talking about. So, what I would do is if I wanted to figure out exactly how high. Oh, okay. I'm sorry. I'll get you guys your Filter Fest grades. I'm going to do that today. Don't worry about it. You guys did a great job, by the way, for Filter Fest. All right. But anyway, with rock climbing, I would take the rock and I would drop it off the cliff, and I would count 1, 2, 3, and then I would hear a splash or something like that. Okay. Or I would take out my watch and I would drop the rock off the cliff and I would time it. 1, 2, 3, whoop, and that would be like 3.25 or something like that seconds. And then from that, you can actually figure out how high that cliff was just by knowing how long it took to fall to the ground. And would you like to know which equation I used? You can use this equation right here, because this tells you the height. The height, if you know the gravity and if you know the time. That's it. That's all you use. Does that make sense to you? So let's pretend that it took 3 seconds. Okay? All right, fine. Then my height is equal to 1/2 times gravity. By the way, I didn't tell you what gravity was. Gravity is actually 9.81 when measured in meters, times 3 squared. All I did was I plugged in the values into my equation, and I just said, pretend like I dropped something off a cliff and it took 3 seconds. Are we cool with that? All right. So this is actually 1/2 times 9.81 times 9. Do you guys know where I got the 9 from? That last 9 in the end? Nope, no idea. Jonathan's got it. It's because 3 times 3 is 9. You see that 3 squared? That's 3 times 3, which is 9. We're cool with that? And by the way, I don't expect any of you to do any of these calculations in your head. So somebody please use a calculator. What is 0.5 times 9.81 times 9? I don't have a calculator on me. Please use a calculator. All right, here. It was this. I'll show you. It was here, search. 0.5 times 9.81 times 9. 44.145. That's it. So, apparently, if something takes 3 seconds to fall, you would be standing at 44.145 meters. Yes, we are archiving this. Okay, that's it. That's how you would use this equation right here. H is equal to 1/2 g times t squared. And this came from that super complicated equation, which wasn't very hard to actually. You know what I mean? It wasn't that hard to begin with. So what I'm trying to do is, like I told you, I'm taking this super complicated math and I'm trying to make it as straightforward and simple as possible for you folks. And I need you folks to stop me without making a big joke out of it, but actually stop me if you are confused. But if you're not confused, and if you're saying, oh, okay, this makes sense, please tell me so I can make sure I know that we're good here. All right. All right, so check this out. You ready? What if I wanted to do something else? What if I knew how high something is, but I wanted to know how long it would take to get to the ground? For example, what if I went to the top of the Empire State Building and I could look up the height that I'm at, and I drop a penny off of it? I want to figure out how long it will take for that penny to reach the ground. That sounds like a fair question. That's actually a physics question. Does that make sense to you? The problem is we can't use this equation that we have here. We have to modify it a little bit. Because this tells me the height if I know my time. This time I'm looking for the time if I knew the height. Okay, all right, let's work with this thing. I'm going to rewrite the equation. Okay. This is where some algebra comes in, so if you're completely confused, please let me know. The first thing I'm going to do is I'm going to multiply both sides by the number 2. Ask me why.
Why?
Okay, fine. Hoku asked me why. Well, the reason is because I want to get rid of this fraction.
So many people are saying why.
Well, it's because I told him to ask me why. The reason is I want to get rid of this fraction. See this 1/2? See this 2 on top and that 2 on the bottom? Those guys cancel each other out. So that successfully gets rid of my fraction that I don't want to deal with. The whole point of this game is to get t all by itself. By the way, the person that's with me, her name is Hoku. She is a 6th grader who's going to be possibly joining some of our discussions when we have for the Science Olympiad.
Yay.
All right. Yes, and many of you know her, apparently. All right, so I'm going to rewrite my equation down. 2h0 equals g times t squared.
You call me Fuku.
All right. No, Hoku. Hoku, I don't think they heard your name.
Hoku.
Hoku, like turtle. All right. So is anyone freaked out with this equation right here? Are you freaking out? Or is that like, oh, I get it. I understand where that comes from. Okay, Here, I'm going to stop. I'm going to do this slowly. Jonathan, what is freaking you out about this? Reducing the 2. Okay. To get here, all I did was I took this boxed equation up here and I moved the 2 to the numerator on the other side. Because the numerator, the 2 was in the denominator on this side, so I'm just basically multiplying the 2 out. I'm getting rid of the fraction. Jonathan, does it make sense to you now? Yes. We know that Hoku is a turtle.
It's Honu.
Oh yeah, that's right. Honu is a turtle, right?
Honu's turtle, Hoku's star.
Oh, Hoku is right. The Hokulea, right? I'm sorry. I'm so sorry. Yes, this is not the conversation I want to have. I want to talk about this equation that we're talking about.
Focus.
2h0 equals g times t squared. We cool? Yes. All right, good. Now, I want to get t all by itself. There's a g that's blocking it. That g is being multiplied. How do I get rid of that g? I don't want it there. What is the opposite of multiplication?
Division.
Division. So would it be all right if I divide both sides by g? I have to do it to both sides. I need to divide it because dividing it gets rid of this g and this g. Good, I'm getting closer to getting t all by itself. And I have to do it to both sides because that's how you play fair. Are we cool with that? So let me just write this down again. 2h0 over g is equal to t squared. But nothing to freak out about. Right? There's nothing that we did here that's crazy. All right. Here's the only crazy thing that I have that I think is kind of crazy that you guys might not have seen. I want to get t all by itself. The thing that is preventing t from being all by itself is the square. So what is the opposite of addition? Well, it's subtraction. What is the opposite of multiplication? Well, it's division. What is the opposite of squaring something? Now this is where you might not have seen this before. The opposite of squaring something, no, cubing something is if there were a 3 up here. No, that's not the opposite. The opposite, the thing that fights a square, is a square root. That's where the square root comes into play. Have you vaguely seen something like this before? Maybe not seen this, but at least now you can say, oh, okay, all he's doing is he's trying to get rid of that square, the t squared. I don't like that 2 up there. I want to get t all by itself. So in order to get rid of the square root, or in order to get rid of it, I take the square root. Using Jonathan's example, if I have 3 squared, I'll get 9, right? What if I wanted to figure out, well, what is the opposite of that? You take the square root of 9, and what do? You get back 3. It gives you back what you started with. It undoes the square. The square root undoes the square. Does that make sense? Because we're cool with the square root of 9, right? Have you seen that before? The square root of 9? It's basically 3 times 3 is 9, so the square root of 9 is 3. Does that make sense to you? So the square root actually undid what the square did in the first place. Okay, so here's my answer that I have. T is equal to the square root of 2h0 over g. And that's 2 times h0 over g. By the way, just to let you know, all of this is literally typed up for you in the lab. That's where all of these equations come from. Look, that's it right there. T is equal to the square root of 2 times h0 over g. So, you don't have to freak out. It's in fact, not only is it typed up for you, but I explain each step. All I'm doing is I'm actually going through this thing with you personally, one-on-one with you, so I can answer and head off any questions that you might have, so you don't freak out when you look at this thing. But I spent the time. It took me all morning to type this thing up for you. Typing the math in here is crazy. All right. So now, here's the beauty of it. We now have an equation to figure out how long it will take if you know how high you started at. So let's answer our question that we asked way back when. Let's look up some information real quick. What is the height? Dear Google, what is the height of the Empire State Building? All right, here we go. The Empire State Building is 1,250 feet tall. Let's see. The roof height, which is where I'm assuming we're standing. We're not going to stand on the antenna. The roof height is 1,250 feet tall. Okay? Or 381 meters. Those are the same things, it's just different ways of measuring it. So, if we want to figure out how long it will take, we take the time, and that's equal to the square root of 2 times the height. And what did I say the height was?
250 feet.
No, 1,250 feet, or 381 meters. By the way, which one? Oh no, it was 381, right? Or 360? No, it was 381 right here. 381. All right. Which one am I using? Am I going to use 1,250 or 381? Well, because we're doing science, and science always uses meters, let's use that. So I multiply that by 381, and I divide it by 9.81. Because gravity, as I told you before, when you measure gravity in meters, it's 9.81. Right? That's something you might want to write down. And you guys keep saying it's 361, but no, it says the roof height is 381. I don't know where you're getting 361 from. It's right there. It says 381. That's an 8. All right, anyway. Yeah, don't worry about it. Okay, so let's calculate this out. I'm curious to know how high this is. So, by the way, don't get this dot right here confused with this decimal. That is not 2.8 or 381 divided by 9.81. Those are different things. This is 2 times 381 divided by 9.81. Okay? All right. Dear Mr. Google, what is 2 times 381 divided by 9.81? And I think it's actually Yahoo's who's giving me this answer. Dear Mr. Yahoo, Dear Yahoo, what is 2 times 381 divided by 9.81? It's that number. Got it. What is the square root of that? So I'm just going to put in SQRT. Put it in parentheses so it knows what I want to take the square root of. So it basically says, I want to find the square root of this. 8.81. Apparently, it will take you 8.81 seconds. If you were to jump off the Empire State Building, don't do it, by the way. Not recommended. I'm not advocating that whatsoever. Don't say, well, Mr. Dalday said. But if you were to jump off the Empire State Building, it would take you 8.81, almost 9 seconds to hit the ground. Ho, ho. All you guys are doing your video cameras. Okay, wait a second. No, we don't need it. We just, Mr. Dalday's here. Or if you were to drop a penny off of the Empire State Building, it would take you 8.81 seconds for it to hit the ground. And how did I figure that out? Using my magical formula, which wasn't really magic. Does that make sense? It wasn't super crazy. It was actually pretty straightforward. All right. So, this quiz, which is your first quiz that I want you guys to do, and apparently it's due on, I don't know when it's due. I think it's due on the 19th. Wait, why does it say attempt due 2016 in January? What? I'm going to edit that right now. That doesn't make sense. January 5th, 2016. What? No. It's not due then. It's due October 16th, 2015. It's due on the 16th. It's due on Friday. Anyway, whatever. I don't know what the deal is. Oh, I see. Quinn wanted to show his face so that you can see if you remember him. Not the time. Okay, not right now. Why not? All right. So, here's my first question for this lab. If you were to drop an object from exactly 1 meter, how long would it take to hit the ground? All you do is you plug in 1 meter into this equation up here. And you do the exact same thing that I just showed you how to do, but instead of putting 381 meters for your height, you put in 1. That's it. Does that make sense to you? Is it crazy? No, it's not crazy. It makes perfect sense. Then what I want you to do is this. Then I want you to experiment with my equation, because Mr. Dalton's equations are cray-cray, right? Like, these equations are crazy. I don't believe you. So here's what I want you to do. I want you to find a meter stick or some kind of ruler. And I want you, by the way, 1 meter is about 40 inches. So you take a meter stick and you drop something and you time it. How long does it take to hit the ground? You just drop it. That's all you do. You drop and say, click your stop. Actually, here we can even do this experiment. Here's a stopwatch. Do you know how to use a stopwatch? Start, stop. Okay. You got to time it. It's going to be quick. Ready?
Set, go.
What is it?
Probably about 58 seconds because I pressed a little late.
No, it's not. It's 0.59 seconds. Or 0.58 seconds.
0.58 probably because I just...
Good. 0.58 seconds. So you just time it. Okay? And you can't put anything inside of inside of this table, but what you can do is I ask you, what is your measured time for trial 1? So then we would type in 0.58 seconds. And then we do it again. And we do it again. And we do it again. And that's what science is all about doing, is you're repeating your trials to make sure you're getting good data. So you repeat your trials 5 times. Okay? And then I ask, what is the difference between your first trial and the time that you calculated? So the first thing I asked you to do was calculate out exactly how much time it would take. And then you'll get some answer. I don't know what the answer is. Actually, I do know what the answer is, but I'm not going to tell you. You'll calculate it out. You'll figure out exactly how long that would take. And then what you do is you measure a whole bunch of times. And then you find the difference. How do you find the difference of something? If I have one time and I have another time, how do I find the difference between those two? I subtract them. Very good. By the way, I'm only looking for a positive number. So if you get a negative number, just put in the positive version of it. And that would be answering these questions right here. What was the difference between the measured time and the calculated time for trial 1? Good. Easy to do, right? Okay, do the same thing for trial 2, 3, 4, and 5. What is the average for your measured time of all your trials? Do you guys know how to find an average? Yes, easy. All right. How do you do it? Because I'm not sure Hoku knows how to do it. Do you? You add and then divide. Exactly. For example, I'm just going to make it up off the top of my head. If we have 0.34 and 0.47 and 0.58 and 0.62 and 0.39 or something like that. These are all of my measurements for my time. I measured the time in it 5 times and it took me that. What I would do is I would add all of these numbers. No, there's only 5 of them. You don't need to write this down. I'm just giving you an example. You would add them all up. And then you would divide whatever you added by. And I'm going to put a parentheses there so you make sure you add them all up first. Right? And then you what do you do to it? You divide it by what? By 5. How come 5?
Because that's how many numbers.
Because that's how many numbers you added in the first place. You know how to take an average.
Well, I think I know how. Just in my math book, they don't call it average.
They call it the mean.
Yeah.
Yep. That's what it is. I want you to find the mean of this. Of your answers. You divide by Doritos. Oh, I wish I had Doritos to divide by. All right, so I want you to find the mean average of these numbers and these numbers right here. The calculated time is going to be the same. So really your average is going to be whatever the calculated time is. But yeah, you don't need to fill in this table. I just put the table in there to help you out. I'm actually just asking you questions about the table, about each entry that you put into the table. Got it? Yes. All right. You guys are starting to revolt. Technically, I have 15 more minutes left, but I feel like I've covered a lot of material. Okay? Let me do this just to recap, all right? Just to kind of show you, hey, this is what we covered. All right? So I'm not going to cover anything new. I'm just going to take 5 minutes and just say, all right, let's calm down, and I'll recap on what we covered. Got it? All right. So, today, you learned about this crazy equation. You don't need to write any of this down. I'm writing it down for you. This crazy equation, which turned into this. It turned into that. Because y is talking about the height, so we replaced it with an h. Y naught is talking about the height that it started at, so we replaced that with an h naught. The a is talking about gravity, which is in the negative direction, so we replaced the a with a negative g. That's where that comes from. We cool with that? The next equation that we came up with was this. I think it would look something like this. H naught is equal to 1/2 times g times t squared. This equation wasn't pulled out of my butt. It was actually came from right here. It came from the above equation. All right?
Uh-oh, he killed somebody.
Oh, sorry. All right, this equation didn't come out of like just nowhere. It actually came from right up on top. It's not a totally different equation. It's really the same equation. We just kind of tweaked it a little bit. And really, this will tell you the height if you know the time it takes. So this will tell you the height that something is at if you know how long it will take. For example, we dropped a rock off of a cliff and it took 3 seconds, and apparently if it takes 3 seconds to hit the ground, then the height that you were standing at was 44 meters, and we calculated that today. Okay. We also messed with this equation a little further, and we got this equation right here. T is equal to the square root of 2 times H naught over G. Yeah, that's the one. Yeah, actually, Isaiah, this is exactly like functions. This is what a function is. It's telling you the time. Now, this is a different type of function. This is telling you the time as a function of height. This is telling you how long it would take if you knew the height of something. And this equation didn't come from mid-air or craziness or magic. It's really just this equation above shuffled around a little bit. That's all it is. And all of these equations really just come from this. I just shuffled them around a little bit. And I showed you how to shuffle them. I showed you each step, so it's not freaky to you. You haven't died doing any of this stuff. I haven't hurt you yet. No, it's not even really. I don't know. The math to me isn't that bad. I'll be honest with you though. I majored in this stuff, so this is what I got a degree in college. All right. And this tells you the time if you know the height. For example, if we knew the height of the Empire State Building and we jumped off, we can calculate exactly how long it will take for us to hit the ground. Apparently it's 8.81 seconds. Are we cool? So, I am going to have you folks do labs that use these equations. And that is how I'm going to teach you about trajectory. Because trajectory can be very confusing. It can also be very cool. All right? Now, I'm not going to talk about math. I just want to let you guys know. For the air trajectory competition, for those of you who want to participate in the Science Olympiad, I'm going to have the entire class do labs that have to do with the air trajectory competition, but not everyone needs to participate in it. You guys can choose whether or not you want to be in the bridge one. You guys don't need to participate in any of these at all if you want, but you do need to do the labs that I have set up for you. But apparently, we need to design something that will launch a tennis ball. There's my cannon. I'm going to make it like out of a pipe. A tennis ball, and launch it so that it lands at a certain distance x. And I think this distance is between 2 and 8 meters. And the way we need to do that is we probably need to have a little, like, I don't know, I'm just going to put a bag there. A bag where you're going to have some really heavy mass, which apparently is like 15 kilograms. No, not 15. I think it was 5 kilograms. You guys can look it up. But anyway, it's 5 kilograms, which is about like 11 pounds. Drop onto the bag, forcing the air out, forcing the tennis ball out. And we need to calculate exactly where this thing lands. Actually, what they're going to do is they're going to give us a little target right here. Like a bullseye. They're going to give us a little target, and we need to figure out how to shoot that target with our air-powered cannon. That is what the competition is about. I want you folks to start thinking about how you might want to design something like that. It looks pretty cool to me. Got it? No, we're not using any kind of explosions. No, nothing is allowed to be radioactive in the competition whatsoever. In fact, you have to read the rules, and when you read the rules, you'll figure out that we're not going to be using any explosives or anything whatsoever. Oh, come on, this is still really cool. Yeah, no, sorry, no gunpowder. Sorry. Okay. Class is done. I'm done. You're done, apparently.